A pleasant morning to each and every one of you. I am Rizal M. Baterzal, and together with my co-presenter, Mr. Sammy Delangan Jr., we will going to discuss to you what is earthquake and how it affects urbanization. So this will be the content of our discussion. First, we will going to discuss to you what are earthquake and urbanization means. Next are the factors affecting the oscillation of earthquake. And lastly, what are the roles of engineers in preventing collapses during an earthquake? So earthquake. An earthquake is a sudden and violent shaking of the Earth's surface caused by the movement of the tectonic plates beneath the Earth's crust. It is a natural phenomenon resulting from the release of accumulated stress along fault lines. Earthquakes can occur along plate boundaries where tectonic plates interact or within the interior of tectonic. So, an earthquake is a natural event characterized by a sudden and intense shaking or trembling of the Earth's surface, which is caused by the movement of tectonic plates and the release of accumulated stress along the fault lines. So, it results in the rapid movement of the Earth's crust, leading to ground shaking and potentially causing damage to structures and landscapes. Urbanization. Urbanization refers to the concentration of human populations into discrete areas. This concentration leads to the transformation of land for residential, commercial, industrial, and transportation purposes. So in simple words, urbanization means more and more people moving from rural areas or the countryside to live in cities and towns. So this leads to cities getting bigger and busier as they build more houses, stores, factories, and roads to accommodate the growing population. So earthquake and its effect to urbanization. Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. So when an earthquake happens, it can cause a lot of damages. The effects of earthquake on urbanization are also straightforward. It can damage or destroy buildings, roads, and other infrastructures in cities. This makes it challenging for people to live and work there. So earthquakes can slow down or even reverse the growth of cities and urban areas because they disrupt daily life and can be very costly to recover from. So how do buildings collapse during earthquake? Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. So the key point here is that it is not the initial shaking of the ground that directly causes the buildings to collapse. Instead, it's how the building directly responds to that shaking with the foundation displacement and subsequent vibrations that can lead to structural failure during an earthquake. Thus, proper engineering and construction techniques are crucial in designing buildings to resist these forces and ensure they remain safe during seismic events.
The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to certain amount of displacement. Along with the building's material type and the shape of its column, stiffness is largely a matter of height. Shorter buildings tend to be more stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible, but the 1985 Mexico City earthquake is a good example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged, and the mid-sized building that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, the frequency is how many back and forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around, including a building's mass slowed down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing the relationship, stiffness and the natural frequency are proportional to each other, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid-sized building. Like a well-timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even farther back, eventually reaching a far greater extent than the initial displacement. Today, engineers work with geologists and seismologists to predict the frequency of earthquake motions at the building sites in order to prevent resonance-induced collapses, taking into account factors such as soil type and fault type, as well as from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to the structures that are shorter and stiffer. Engineers have always devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibration. In the end, it's not the sturdiest buildings that will remain standing, but the smartest one.